So let's talk about random variables. And they follow a probability distribution like I was talking about yesterday. There's special types of probability distributions we'll get in towards the end of the unit. But for the time being, let's talk about what random variables are, the types of random variables we can have, as well as how problem solving use them. So as an example, we toss a fair coin 3 times. And there you see the possible outcomes. There are 8 of them. You get all heads, first 2 heads, tails, etc., all the way to all 3 tails. Okay? So from this problem, we can define a random variable. And in this case, the random variable is going to be the number of heads. I could have defined another random variable and talk about the number of tails. But we're going to talk about the number of heads. Okay? And so we can summarize all the possible outcomes using a probability distribution, which we have before. Okay? So we have 8 possible outcomes. How many of those outcomes, this random variable can only take on 4 values? No heads, 1 head, 2 heads, all heads, or 3. What's the probability of getting 0 heads? If you look at all the possible outcomes. 1 out of 8. Because we could get all tails, that only happens once. All the other ones have at least 1 head in them. And then if we want to go to decimal, we can. That's 0.125. What's the probability of getting 2 heads? Well, 1, 2, 3, yes. 3 out of 8, which is going to be 0.375. Oh, sorry, that's 1 head is 3 out of 8. I jumped ahead. Here's the ones, three possibilities where there's 3 out of 8. 3 possibilities where there's 2. So it's the same probability as if there's 1 head. And then finally, 1 possible chance out of 8 that we get 3 heads or all heads. So that's our probability distribution. And remember, we talked about it being valid. Yes, it is valid because all the probabilities add up to 1, and each probability is between 0 and 1. Okay? So the definition of a random variable, it's a set of possible outcomes that haven't occurred yet. And each of those outcomes, however we define a random variable, okay, has a certain probability of happening. You know, like, so I could say, what else could I do? I could roll 2 dice, and say define a random variable as that the sum will be an odd number, or that the sum will be an even number. Okay, and how many different ways can I get odd numbers? How many different ways can I get even numbers? Same kind of thing. This is also known as a discrete random variable because it takes on a fixed set of possible outcomes, okay, with no gaps in between. Basically, what this means is that the possible values of the random variables are whole numbers. Okay? Like in this situation, there are 4 distinct or discrete possibilities. 0, 1, 2, 3. If it was continuous, that means there's a probability of getting fractions between 0 and 1. Fractions between 1 and 2, and so on, which is impossible. right? I mean, like you can't, there's no such thing as what's the probability of 2.5 heads or 1.79 heads. That makes no sense. It's either 0, 1, 2, 3, 4 possibilities. Continuous could be a whole string, fractions included. So we're going to focus on string right now. And we can answer some questions. So what is the probability that x equals 0? The probability there will be 0 heads. What is that? 1 over 8. Or 0.1. What does px less than or equal to 2 mean?
2 less than 2 or 0. 0 and 2.
Right, the probability of getting 0, 1, or 2 heads. Okay, so 0, 1, or 2 heads. And what is that probability? Well, we would just, the probability of 0 heads is 1/8. 1 head is 3/8. 2 heads, 3/8. Add those together to get 7/8. Or if we want to go to decimal, 0.875. How would you use, or how would you use notation to answer this question? The probability of getting at least 1 head. X is greater than or equal to, right. Remember, at least means at your starting point and more, not at your starting point and less. Sometimes students get that confused. So what is the probability that it's going to be 1 or greater? Well, it's going to be 3/8 for 1, 3/8 for 2, 1/8 for 3, and once again, we get 7/8. Or if we go to decimal, 0.875. Okay. Okay. Here's another example where we use discrete random variables. Not sure how many of you are familiar with the game of roulette, but there are 37 spaces on a roulette wheel, and you spin the wheel and you throw a ball, little metal ball inside, see where it lands, and then you get to bet on what color it ends up, what number it ends up. There's all sorts of bets you can place. Okay. So our situation is we're going to let X equal the winnings from a $100 bet on black. Okay, so that's our random variable. Thank you. Is black. Getting black. So if we get black, we get 100. We get red or green, we lose 100. So what's the probability of getting 100? 18 out of 37. Which is about 0.486. And therefore, the probability of not getting black is 19 out of 37. So slightly less than 50-50 chance. Okay. All right, talking about expected frequency and expected value. Normally you don't just play once, you play many times. This is a little ridiculous. But if you were to play 1,000 times, how many times would black be expected to win? How would you find that? Don't need to cross multiply. Wouldn't we just take, this is the probability of getting 100 one time, 1,000 times, 5,000. We would expect that if we played 1,000 times, we would get black 486 times. Doesn't mean that's going to happen, but it means according to probability theory, that's what we expect would happen. Okay? Let's take this a little further with expected value. If I were to play that 1,000 times, what would my average winnings be? So you got to be a little careful. Any idea?
Plus 1,000 minus 36.
Say again.
46.
Yeah.
Plus, what is it, 5 and 14 times negative?
Good. Okay, so it would be, this is what happens if you win. 1,000 times, you expect to win 486 times, you win $100 each time. However, there's another situation, isn't there, where you lose. So what's the probability that you lose 1,000 times? Well, it's 514 times 1,000, 0.514 times 1,000, which gives you, there's 514 times where you're not going to get black. And when that happens, you lose 100. And this or this could happen, or means add. So we get 48,600 minus 51,400 gives us negative 2,800. So if we played 1,000 times, now be careful how you read this because we were asked for the average, right? So if we played 1,000 times, we'd expect at the end that we'd be here, out 2,800 bucks. Okay. So what's that on average? I would have to do negative 2,800 divided by 1,000. And these are actually dollars now, negative. I would expect every time I play, I'm losing $2.80. Okay. Now that obviously doesn't make sense because you're not going to lose $2.80 every time you play. You're either winning 100 or losing 100. This is over the long run. This is if you played many, many, many times. On average, this is how much you would you be losing. Would you play this game? You would? Yeah, because you just think you know it's going to be a winner. You just got a feeling, right?
Exactly.
Yeah, and feeling is incredibly important in probability. Okay, yes. Haven't quite quantified how emotion is calculated into probability, but I hear they're working on it. Yeah.
They should be working.
Oh yeah, yeah. I'm sure you could measure your emotional intelligence and maybe divide that by the square root of. Okay. So what we just calculated was the expected value. So the expected value is the average value of a chance process after repeating trials.
do it over and over and over again. Okay? So how would we interpret? Because remember in statistics, we like to interpret. After many trials, you want to add that. Or after many spins, because it's specific to a roulette wheel, you would expect to lose $2.80 on average. Okay. And we've already answered this question. Okay. Because you don't lose $2.80 per spin. You lose an average of $2.80 over many spins, in this case, 1,000. So it's talking about the average loss or gain, depending on the game. Right? Okay, so how do we calculate expected value? Well, the way we did with that example, we took all the probabilities that were possible times their payouts, right? So like there were only two possibilities in the previous example. So we took the probability of winning times its payout of 1,000. Then we took the probability of losing times its payout of negative 100. So using that, we can develop a formula. For finding the mean of a random variable or its expected value. Okay? So to find this, and we either use capital E then X, which means expected value of the random variable X. Or remember, we use this symbol for mean, mu, the Greek letter, of the random variable X. You can see it that way. Either one of those is found by multiplying each possible value of the random variable, okay, times its probability, or the probability times its payout. So we would do this. So whatever the value of the first one is, times its probability of happening. Whatever plus the probability of the second times its probability, etc. Depending on how many possible random variables there are.
What is that letter?
Which one? This one?
Yeah,
Mu.
but that's not how I write it. Is that okay? Should I like?
How do you write it?
I don't have extra down on it.
Like it's kind of a weird looking M. Right? Like it does look almost like a capital M in a way.
Okay.
If you want to exaggerate those.
Yeah, down. You just gotta leave it like that.
Yeah. Okay.
Should we write it like you, or should we write it the way you write it? No, I tried to copy yours, so mine, like this. This is not natural. That
Yeah, you're fine.
is not natural.
Okay. Do it naturally.
No pressure. Wait.
Do it naturally, no pressure.
Like that.
What the quality is that?
Is that bad? I should write it like that. Look, I almost wrote it. Even though I tried.
All right.
Is that good?
Wow.
No, but I mean, like, would you be like, would you understand what I mean if I wrote that?
Yes, because in the context of the question. Okay, but we don't want to write the formula using all of this. We want to show just that we're taking each one, taking each value of the random variable, multiplying by its probability, then adding them all together. What was that symbol that we used for adding all together? Sigma, capital sigma.
Yeah.
So we're going to take each one, and I'm going to call it xi, each random variable, because we don't want to do 1 or 2. We're going to just, because I could be 1, 2, 3, 4, etc. Times its probability. And that is the formula you will always get.
Will I ever have to write sigma on a piece of paper? Like, would I ever have to use that symbol? Because I don't remember to write it.
Copy like I did it.
Very, very normally. Yeah.
Okay. So let's use this formula in some examples. Coin toss. Let's do some coin toss. Heads means you get 100, tails means you lose 100. What is the expected value? Well, two possible situations, right? So EX or UX. How would I do it? Positive 100 times 0.5 minus or plus negative 100 times 0.5. And hopefully you can see that equals 0. It's a completely fair game. Okay. So you might come out on top, you might come out on the bottom, but over the long run, if you do it many, many times, you'll end up where you start. This one, same toss, except this time if you get heads, you win 300. Hopefully you're seeing, oh, this is a better game for me. And remember, it's all about me. It's not about the welfare of society and that could decay because of gambling. But I digress. But it would look like this.
Ooh, I think our chances are higher.
So this would give me $100. And that's $0. I have to answer. Yeah, much better. Much better game. Okay. Really good chance you're coming out on top. You can buy your steak dinner at the McPhillips Casino. Although I doubt they would have this game. How about this one? Coin toss again, but this time the coin is weighted so that the chance of tails is greater, 75%. Heads means you get 100, tails means you lose 100. Hopefully you're looking at that saying, yeah, I don't think so. Because, well, heads you win 100, what's the probability that you get heads? 0.25 minus losing, well, minus 100 because you're losing 100 times its probability of 0.7. Definitely not good. That gives us negative $50. Remember what these values mean. if you played many, many, many times, on average, this would happen here, this would happen here, this would happen. All right. This one maybe not so clear just to look at. So it's weighted again, but now we're back to heads, you get 300. Hard to tell if this is a good game to play or not. Initially, you get 300, but there's only a 0.25 chance of occurring. Lose 100, and there's a 0.75 chance of that occurring. And what does that give me? 0, I believe. So the bigger win output is counterbalanced by the weight of the coin in favor of tails, so that eventually it becomes nothing. Okay, this last example here. So remember, we're back to our roulette, and the probabilities are still the same. Getting black, 18 out of 37, or 0.486. Red or green is 19 out of 37, which is 0.514. We calculated the expected loss for 1,000 plays. Remember, it was 486 times 100 plus 514 times negative 100. And if we played 1,000 times, we'd expect to lose $2,800. And what's the expected casino profit? $2,800. Our money's got to go somewhere, and it's going to go to the casino. Okay? So casinos bank on many, many trials, and people play a lot. Okay? So they profit through long run expected values, not short run. Right? Because I mean, like if you just went and played once, you win 100 or you lose 100. They're expecting you to play several times so that it starts to average out that you're losing, and whatever you're losing goes to the casino. Okay? And of course, I mean, that's not the only reason. They also want to base their games on that they have maybe a better chance of winning than you do. Although it doesn't look like that. It doesn't appear so. Okay, but in the long run, that's what's going to happen.
Like, what do they do? They make the point?
Well, no, like the games that they use, right?
Oh,
You know, like the card games.
yeah, like,
Things like that. I mean, obviously, they don't want to come up with card games where the probability of them losing a lot every time happens. So, I mean, these card games have been around for so long, poker and blackjack and bumper. And then other things like the slot sheets. Slot sheets, right?
how do I open my own casino?
How do you open your own casino?
Where do I get a permit?
I would imagine you can contact the city of Winnipeg,
Yeah, let me know.
just say, I'm going to open my own casino. What steps do I need to take?
Okay, deal.
I mean,
You're all welcome to come.
let's see here. Well, we might as well keep recording this. Okay.
How to open a casino in 19 simple steps.
How to open a casino in Winnipeg.
Oh, you have to apply for casino. Oh, Oh, you have to do not sort of casino, all right, check local regulations.
Check local regulations, ensure that,
I don't. Do you think they would let me open one even though I'm not a Canadian?
yeah,
Definitely not.
why not?
Definitely not.
Have you ever heard of foreign investment?
Alright.
Why wouldn't it be?
But I would be paying taxes.
Yes.
Yeah, okay, all right, so what's the next step?
Feel
Construction,
free to read.
investment, I already have my investors.
Who are your investors?
You guys.
Really? How much do you expect us to put up to build a large casino that will cost millions? Oh, your boarding room.
Oh.
I'm thinking you don't even have to worry about the government because you're going to hit an obstacle right away. What do you think that obstacle is going to be?
Oh, it's been gone.
Well, not just her. I think the head of school will probably say it too. Why are you looking at me like that? No, she wouldn't. Do you have any grasp of the moral difficulties of opening a for-profit casino in an educational environment? Those of you who decided to watch this video or searched it out, hopefully you learned something from this latter part.